Hello everyone, welcome to the course on Emerging Domain Electronics Engineering. This is lecture 3 and in this lecture we will see the bipolar junction transistor, which is also known as BJT. So in the last lectures we have seen the two terminal devices like the P-N junction diode, Zener diode. Now we will start with the three terminal devices which is known as bipolar junction transistors. So first let me start with what is bipolar here stands for. The term bipolar means the flow of current due to the different charge carriers, means the minority as well as majority charge carriers, means the electrons as well as holes. If in a device the current is due to only either the electrons or due to holes, so that type of device is known as unipolar device, like FETs, which is called as field effect transistors. So we can say BJTs are bipolar devices, whereas the FETs are unipolar devices. Means in BJT the current is due to both majority and minority charge carriers. Now we'll start with the construction part, how a PN junction, how the BJT is constructed. So a transistor is basically constructed with the help of three different type of semiconductors. Let's say if we are taking two N-type semiconductors and one P-type semiconductor is sandwiched between two N-type semiconductor, then it will result in a formation of NPN transistors. And we can have two P-type semiconductors, and in between if we are sandwiching one N-type semiconductor, then it will be known as PNP type transistor. So we have basically two type of transistors, which is NPN and PNP. So we'll start with the construction here. That in the construction part we can say that in a bipolar junction transistor it consists of three terminals. One terminal, first terminal is known as emitter terminal, which is represented as capital E. Next we have the base and we have the collector. So it is a three terminal devices. Likewise in the diodes we have only two terminals. So let me start with the emitter first. So emitter, it is the first portion of the transistor, or it is also known as, it is the one side of the transistor that supplies the majority charge carriers like electrons or holes. If the material is of N type, then it will be supplying the electrons. If the material is of P type, then it will be supplying the holes. So emitter means it will basically supply the majority charge carriers to the other two portions of the transistors. The other two portion here reflects the base and the collector side. So if emitter has to supply the charge carriers to the other part of the transistor, then the doping profile of the emitter has to be heavy, means the emitter is heavily doped. So in the PNP transistor we can say that the holes are supplied by the emitter terminal. Similarly in the NPN we can say that the electrons are majority in the emitter region and they are supplying to the base and collector region. Now we will talk about the collector. Collector is the other portion, the other side of the transistor. So it is the portion which basically collects the charge carriers. What type of charge carriers? Again we have two type of charge carriers like electrons or holes, depending upon NPN or PNP. So the doping, because the collector has to collect the majority charge carriers, so the doping profile of the collector is moderate, means it is neither heavy nor it is lightly doped. So the doping profile will be between a heavily doped and a lightly doped. We'll see in the next slide that base will be lightly doped. Also I want to add one more point in this, that collector area is large in comparison with base and emitter. So this is also the part of construction. Now we'll talk about the base terminal. The middle portion between which basically forms the two p-n junctions. We will see here that bipolar junction. What is junction? What is the meaning of junction here? So there are basically two junctions formed between emitter and base. This is called as first junction, emitter base junction EBJ, and the other junction which will be formed as collector base junction, which is between the collector and base terminal. So the base of the transistor is thin as compared to the emitter and the collector. Also, the doping profile for the base is lightly doped to minimize the recombinations. Also, the width of the base is thin to minimize the transit time effect, because if the base width is very small, if this is small, so the charge carriers will take very less amount of time while moving from emitter to the collector side. So here we can say that the base is thin, also the doping profile is light. So collectively we can summarize the construction part here, that first the emitter terminal is heavily doped because the role is to supply the majority charge carriers. And if we talk about the area, so the area for the emitter is moderate, whereas the collector is moderately doped but the area is largest, while the base is thin and lightly doped. So this is under the construction part. Now there are basically 4 modes of operation of BJT depending upon the junctions. We have already seen that there are 2 junctions. One is called as emitter base junction EBJ, and another one is called as CBJ, collector base junction. So first is the forward active mode. So forward active mode stands for when we can say that the emitter base terminal is forward bias and collector base junction, this junction is reverse bias, then it is called as, then this mode of operation is known as forward active mode. And generally the application of BJT is that BJT can be used as an amplifier. BJT can be used as an amplifier. It will amplify the AC signals which we have applied to the circuit. So generally we use this configuration, we use this mode for the amplifiers. Next is the cutoff mode, when both emitter base junction and collector base junctions are reverse bias. Then we can say that there is no current flowing through the transistor and the current is nearly equal to 0. And we can say that the transistor is basically working as a switch, and when there is no current flowing through the switch, then it can be treated as open switch. While we have the saturation mode, in this particular mode what we can say that both the junctions are forward bias, emitter base junction and collector base junction. So we can say that in this particular mode there is a saturated amount of current, flows through the transistor and the transistor will turn on. So basically we can say that again in the saturation mode transistor will be working as a switch. We assume that the switch is closed now. So these are the 3 main important modes of operation of BJT. We have a 4th mode of operation which is called as reverse active mode. So in this reverse active mode, this is just opposite of the forward active mode. So what we can say here, that in the reverse active mode emitter base junction is reverse bias, whereas the collector base junction is forward bias, means the opposite of forward active mode. So in the previous one, in the forward active mode, what we have seen that it is basically working as an amplifier. So here in this reverse active mode we can say that it can be used, this mode can be used for the attenuators. So basically we have studied all 4 mode of operations here. Out of these 4 modes, we can say that the forward active mode is quite important because we generally use BJT, bipolar junction transistor, as an amplifier. Because we are already aware that if we want a switch then we can use a diode also. Under the forward bias region it will be turned on, and during the reverse bias region it will be turned off. So now after the construction part and the modes what we have studied here, we'll start with the operation of the transistors, how a transistor works. So first we'll consider here the active mode of operation. Means the active mode is emitter base junction, EBJ is forward bias, whereas the collector base junction is reverse bias. So here we are starting the operation of the transistor with the PNP. We are taking the PNP transistors. Means emitter is of P type. Here we have N and here also we have P. So emitter and collector both are of P type, whereas the base is of N type. So we have two voltages, one is at emitter base terminal and the other voltage is applied at collector base terminal. So we are not going to analyze directly both the effects of emitter base and the collector base voltage. So first we are considering the emitter base voltage, and we are just opening a circuit at the collector base terminal. So this collector base terminal is open circuited, and we are seeing the effect of only the emitter base voltage EB, or we call it as VEB. So what we can say that when the positive of the battery is connected to P side, so the junction here, the emitter base junction EBJ will be forward bias, and when the emitter base junction is forward bias, we are already aware that the width of depletion region is very narrow. So depletion region is narrow. So that when the depletion region is narrow, we can say that the majority charge carriers, which are basically holes, in the P region we are aware that holes are majority charge carriers, whereas electrons are minority charge carriers. So this positive of the battery will basically pressurize the holes which are basically majority charge carrier in the P side, and they'll try to move towards the collector side. So here we have seen that emitter is basically supplying the majority charge carriers, which are holes. So this we have drawn a arrow here by showing that this is a flow of majority charge carriers like holes. Now we will see, we are removing the emitter base voltage and we are applying the collector base voltage VCB here. So while we are applying the collector to base voltage, what we can see here, that as VCB increases, the width of collector base junction CBJ increases because it is reverse bias. So as we are increasing more reverse bias, the width of depletion region increases. So we can see here that collector base junction, the width is high in comparison with the emitter base junction. So in this situation, we can say that the positive of the battery here will basically pressurize the holes. Now what are holes? We are aware that base is of N type, and in N type the majority charge carriers are electrons, whereas the minority charge carriers are holes. So the positive polarity of the collector to base voltage, this will basically pressurize the minority charge carriers present in the base region, and these minority charge carriers will move towards the collector side, and basically collector terminal will collect these holes due to both majority and minority charge carriers. So if we'll combine both the effects like emitter base and the collector base terminal, so what we can see here that we have three different currents. First is the emitter current, next is the collector current, and is the base current. We can clearly see here that we have a broad arrow here which shows the majority current, we have a narrow arrow which shows the minority current. So IC basically the collector current is due to both majority charge carriers and the minority charge carriers. These minority charge carriers are also known as the current is also known as leakage current, and we can represent this by ICO, means the collector current when emitter is open circuited, ICO. And this ICO, this leakage current or the reverse saturation current, this is very, very temperature sensitive. Why this is temperature sensitive? Because we have seen that as temperature increases by 10 degrees Celsius, the ICU get doubles. We have already seen this fact in the P-N junction diodes. So here we have two important equations. First equation is corresponding to the collector current, and second equation what we achieve is due to the KCL, that IE is the incoming current and IB and IC, this is called as the outgoing current. So as per KCL, IE equal to IC plus IB. So this is the operation of PNP transistor in the active mode of operation. Now we have the symbols of these transistors. We have both type of transistors here. First is the PNP and next is the NPN. So how we can distinguish between this PNP and the NPN? On the basis of arrow here, the arrow basically shows the direction of current. So in the PNP, the direction of current is inward, the current is going inside, whereas in the NPN the current is going outward. So this basically arrow shows the direction of current. So after this, these symbols of these NPN and the PNP transistor, we'll start with the various configurations. So there are three basic type of configurations for the BJT. First configuration is known as common base configuration. The other configuration is known as common emitter, and lastly we have the common collector. So first we will see the working of all three configurations. We will see what are the application areas of this common base, common emitter and common collector. Also we will see the characteristics, the input characteristics and the output characteristics. We will see what is characteristics here. So first we will start with the common base. So what is common here? So common here stands for basically that particular terminal is common to both input side as well as to the output side. Or second definition is that common is basically corresponding to the ground. Here we can see that the base terminal is grounded. Also we can say that the base terminal is common to both input side as well as output side. So this particular configuration is known as common base configuration. So we can clearly see here that in the common base configuration, the input current is IE, the output current is IC, the input voltage is what we can say VBE, the output voltage is VCB, which is called as collector to base voltage, like this. So now we'll see what is the characteristic. Characteristic is basically these are the curves between the current and voltages corresponding to the input terminal and corresponding to the output terminal. So here we can see that for input characteristics, what are the variables? The variables are IE versus VBE, and the output symbols here are IC and VCB. IC versus VCB. So if we are drawing a curve between IE and VBE, the curve will be known as input characteristics, and if we are drawing a curve between IC and VCB, it will be known as the output characteristics. For different values of, we will see later on. So first of all, let me tell you what is the input characteristics here. So we are already aware here that the PNP transistor, it can be assumed as a switch. It can be assumed as a two back-to-back diodes like this. So if positive terminal of the battery is connected to P side like this, so the emitter base junction here, EBJ will be forward bias. Means this diode D1 will be forward bias, and this diode D2, this collector base junction, will be reverse bias. So the diode D2 will be reverse bias here. So if first diode is forward bias, then definitely the current IE versus VBE will follow the characteristics which is quite similar with that of a normal PN junction diode. So we can see here that the characteristics are quite similar with that of a normal PN junction diode, with this voltage is, turn on voltage is VB, which is around 0.7. So IE versus VBE. Now before starting with the IE versus VB curve for various values of VCB, means what is the effect on the characteristics if we are varying the collector to base voltage. So we can understand here that there is an effect called as early effect. Early effect. What this early effect says, if we are varying the voltage, collector to base voltage, if we are varying VCB, then we are making this collector base junction more reverse bias. Collector base junction more reverse bias. If collector base junction is more reverse bias, that means the depletion region will penetrate more in the base region. If the depletion region width W increases, then what we can say, the effective width of base, it basically decreases. So once the effective base width decreases, then we can say that the recombinations inside the base will be naturally decreases. So this effect is called as early effect, and this effect was given by a scientist called as James Early. His name was James Early. So he basically elaborated this effect. So we are going to utilize this early effect in the input characteristics of the common base configuration. So how we can utilize? We can say that as VCB increases, the effective width of the base decreases, due to which the recombinations in this particular region basically decreases. If recombination decreases, naturally the current IE, what is the impact on the current? We can say that if the recombination decreases, so IE naturally increases. So we can observe that for a specific value of VBE, we can see that the current increases for VCB equal to 1 volt and for VCB equal to 20 volt. Current increases. So this effect here is called as the early effect. So we have seen the effect of varying the collector to base voltage on the input characteristics. Now we will see the output characteristics. So we are aware that the output characteristics will be between IC versus VCB, IC versus VCB for different values of IE, the input current. So here what we can write down, we can understand this like this, that IC is equal to alpha IE, we'll see what is alpha here, plus ICO. Now what we can say that as VCB increases, collector base junction will become more reverse bias. So if we are assuming that ICO is very small, so we can write down that IC is nearly equal to alpha times IE, or if alpha is nearly equal to 1, then IC is nearly equal to IE. So we can say that if IE is 0, if the emitter current is 0, then naturally the collector current is also 0, so this curve will basically coincide the horizontal axis. Collector current is 0. Next, if we are increasing IE, let's say if IE is equal to 1 milliampere, so what we can say that IC is also equal to 1. If I equal to 2, so IC is also equal to 2 here, means IC is nearly equal to IE. So as we are increasing the value of emitter current, we can observe that the current IC also increases and it is constant. So the current is saturated, current is constant. So we have seen that this particular region where emitter base junction is forward bias and collector base junction is reverse bias, so the region is called as active region. Whereas if we will change collector base, we will change the polarity of collector to base voltage, means if collector to base voltage is negative, then what we can say that this is a diode, if this is a diode and if this become forward bias. So what happen when the diode is forward bias? Current exponentially increases. So we can say that we have the curve like this. So we have different type of curves. But keep this thing in mind that if both the junctions are forward bias, the mode of operation is called as saturation mode. And when the current is 0, when the collector current is 0, so we have seen that when the current is 0, the BJT, the transistor, is acting as an open switch and the mode of operation is called as cutoff. So we have basically shown all the three regions here: active region, the saturation region and the cutoff region. So this is regarding the common base configuration. Now let me discuss further. We have already seen IC is nearly equal to IE in the active region. In the cutoff region, we are already aware that the collector current IC is nearly equal to 0. In the saturation region, we can say that the current increases exponentially. So after these operating regions of the common base configuration, we will be seeing the current gain. What is the current gain for the common base configuration? So this is emitter terminal, base, this is collector. So gain is basically referred as the output quantity by input quantity, and if we are considering the current gain, so current gain is nothing but the output current IC by input current IE. So the ratio IC by IE is known as alpha, and it is the current gain of common base configuration. And also we are aware that IE is equal to IC plus IB. So the value of alpha is basically Typical values of alpha is between 0.90 to 0.99, and ideally what we can say that if IC is nearly equal to IE, then this ratio will be equal to 1. This relationship also we have seen, the current is due to both majority charge carriers and due to the minority charge carriers. So we have basically classified two types of gain. One is called as DC gain and the other one is called as AC gain. So AC gain means this is change in collector current to the change in emitter current at a constant VCB. So we can basically calculate also the alpha AC values. How we can calculate alpha AC? Change in collector current by change in emitter current. We can see from this characteristics that change in emitter current 5 minus 4, and correspondingly here also change in IC. So this ratio will be nearly equals to 1. So after this common base configuration, we'll start with the other configuration of the BJT, which is called as the emitter, common emitter configuration. So as we have seen in the last slides, that the common emitter, here the common stands for that the emitter terminal is grounded or the emitter terminal is common to both the input side as well as the output side. So here the variables are quite important. So for the input characteristics, the curve will be between IB and VBE. IB versus VBE, and the output characteristics will be between IC and this is IC here, and the voltage which is called as VCB, collector to base voltage. So IC versus VCB. So first is the input characteristics. So if this is a polarity here, positive, so positive is connected to P side, negative is connected to N side, we can say that the emitter base junction is forward bias. Now if this emitter base junction is forward bias, so naturally the current will be flowing something like a the current is flowing in a normal PN junction diode under the forward bias condition. So we can see here IB versus VBE. Current basically is flowing like a conventional PN junction diode for a particular value of, let's say, VCE. Now what will happen as we are increasing the value of VCE? So here we can write down that VCE equal to VCB plus VBE. KCL at this junction, VCE, this one, this voltage plus this voltage. Now if we are considering a constant VBE, if this is constant and we are basically varying the value of VCE, so what happened to VCB? As we are increasing the VCE, collector to emitter voltage, VCB also increases. So again we have the similar kind of concept here, the early effect. As the collector to base voltage increases, the effective width or the depletion region width increases, which result in a decrease in the effective width of base. And when the effective base width decreases, due to this the recombination decreases, and when the recombination decreases, the current which is depending upon the base current which is depending upon the recombination, if the recombination decreases, naturally the IB value will be decreases, IB decreases. So we can observe here that if we are increasing the value of VCE, so naturally our IB decreases. So also we have a small equation which we can derive using these two equations. equation number 1, and we have the second equation, IC equals to alpha times of IE plus ICO. We can use this equation number 1 and equation number 2 and will obtain a equation which is IC equal to alpha times IB divided by 1 minus alpha plus ICBO divided by 1 minus alpha. Now if we want to plot the output characteristics which is between IC and VCE for different values of base current. So initially we assume that the base current is 0. IC equals to alpha times IB divided by 1 minus IB, 1 minus alpha plus ICBO divided by 1 minus alpha. We can see this equation clearly. When the IB is 0, so IC equal to ICBO divided by 1 minus alpha. But alpha is very small. Alpha is, let's say, around 0.99. So this ICO is now, it's not a negligibly small quantity. ICO will be quite high. It will not be very, very small. So this curve is bit shifted in the upward direction. Now as further we are increasing the value of IB, as IB increases, so naturally IC also increases. So this curve will be shifted in upward direction like this. Also here, this region is known as active mode of operation. Below this region we have the cutoff region, and to the left we have the saturation region. Now after this we have the current gain, which is called as, which can be denoted as beta. So beta again is a ratio of the collector current, it's a ratio of output current by input current. So as we can see that the output current is IC and the input current is IB. So IC by IB is known as beta DC, whereas beta AC can be calculated as del IC by del IB. So from graphically also we can observe what is the value here. Beta AC, this point, delta IC by delta IB, 30 minus 20. So the value is around 100. So generally the value of the beta, which is the current gain for the common emitter configuration, is near about 100. Now we have a small derivation between alpha and beta. So we can easily derive this beta equals to IC by IB and alpha equal to IC by IE. And by utilizing this equation, we can have the relationship that alpha equal to beta divided by 1 plus beta. Also beta equals to, it's basically like this, 1 minus alpha, alpha divided by 1 minus alpha. So we have the final equation which can be represented as I equal to 1 plus beta times IB, where IB is very small. IB is generally of the order of microampere, whereas IC and IE both are of the order of milliampere. Now these are the applications. Generally the common emitter configuration is used, it is well suited for the voltage amplifications, as we already talked that the transistor BJT is generally used as the amplifier, right? It's at low frequency. Common emitter amplifier also used in the RF, radio frequency transceivers, which is transceiver circuits. Common emitter configurations commonly used in low noise amplifier, LNAs, RF transmitter and the receiver. Now we have the common collector configuration. So as the name suggests, common collector, like this, the collector terminal is common to both input side as well as the output side. The only difference between the common emitter and the collector is these two terminals get interchanged. Emitter and collector terminals get interchanged. So the output characteristics of the common collector configuration is very similar with that of the common emitter configuration. So in the common emitter configuration we have IC as the output current. So here we have the IE as the output current now. So we can clearly observe that the characteristics are very similar with that of a common emitter configurations. Now we can see that the input characteristics which is between IB and VCB, which is quite different. So what happened, as VBE is fixed and VCB increases, collector to base voltage increases, because we can write down the equation VCB plus VBE equals to VCE. So if VBE is fixed, this is fixed, and if VCB increases, so as a result VCE also increases. So the collector to base width increases, which basically reduces the value of current IB. So VCB increases, the curve will going in a downward direction like this. So the input characteristics of the common collector configuration is very different from that of the common base and the common emitter configurations. We can utilize the early effect concept also in this particular situation. The applications now. So the common collector configuration is used in the impedance matching circuits. We can say that the current gain can be represented as gamma equals to output current, which is IE, by input current IE divided by IB, where we can write down I equal to IC plus IB. So we can represent this as gamma equals to 1 plus beta. So current gain for the common collector configuration is very high, which is 1 plus beta, but the voltage gain of this circuit is very small, which is nearly equal to 1. Ideally it is equal to 1, so that's why it is being used in the impedance matching circuits. Also it can be used in the circuit isolation. So now we have a brief comparison here between all three possible configurations of the BJT, which is the common emitter, common base and the common collector. So first we will start with the input resistance. In the common emitter configuration, the input resistance is low, of the order of 1 kilo ohm to 2 kilo ohm, whereas in the common base configuration it is very low. Why it is very low? Because in the common base configuration the input current is very high, because the input current was IE. So if the input current is very high, so naturally the resistance will be very low. For common collector configuration, we have the input current which is IB. So if the input current is very small, so we can say that the impedance or the input resistance of the common collector configuration is very high. Output resistance, we can say that the output resistance is very small for common collector, because the current here is IE, the output current is IE. So the IE is the maximum current, IE is the highest current in all three, so naturally the resistance will be very low. Whereas for the common base configuration, the order is around 500 kilo ohms. Now we'll talk about the current gain. We are already aware alpha, beta and gamma. We have already seen that alpha is nearly equal to 1, so it is very small. Beta is high, we have seen in the numerical that it is around 100, and beta and the gamma is equal to 1 plus beta. So this is also high. We can say that gamma is also high. But the voltage gain, it has been seen that the voltage gain of the common collector configuration is unity, or that's why it is also known as unity gain amplifier. It is also known as unity gain amplifier. So if you want to calculate what is a power gain, so power gain can be obtained by AP equals to AV, the voltage gain, multiplied by the current gain. AP equal to AV multiplied by AI. So here we can observe that this value is high, this is also high, which will result in a high power gain. Also this value is high and this is low. So we can say the value is, normally we can say that it is high, this is high, this is less than 1, so the power gain is low. So we can say that common emitter amplifier is having the highest power gain. Also there is a phase reversal. Phase reversal means that the input and the output signal, they are having a different phase. So in the common emitter configuration, or if we are applying a signal like this, so in the common emitter configuration we are getting a signal which is 180 degree phase shifted. So that's why it is called as phase reversal. In the common base configuration, we have the signal will be amplified, but the phase will be same, that of the input signal. Both the signal having the same phase. Again in this also the signal is having the same phase. So this is a small comparison chart between the common emitter, common base and the common collector configurations. So generally for the designing of amplifiers, will prefer the common emitter configurations, whereas common collector configuration can be used in the impedance matching circuits. Impedance matching, or it is known as unity gain amplifier. So the impedance matching circuit, basically they are used to match the output impedance of first stage with that of the input impedance of the second stage. So in this particular situation we can say that if the impedance of the first stage is matched with the impedance of the second stage, so the maximum power will be transferred to the output side, or the maximum power will be transferred from first circuit to the other circuit if they are connected in a cascaded manner. So this is all about the bipolar junction transistors. In the next lectures we will be seeing about the 4 terminal devices, will be MOSFET. So these are the references. Thank you.